Welcome and thank you for listening to our video abstract of our paper, Graph State Circuit Blocks Control Entanglement and Scrambling Velocities. To discuss this further, let's first talk about complexity, which quantifies the resources required to implement a computation. We can define circuit complexity as a minimum number of 2-qubit gates required to implement a unitary operator which acts on many-body quantum system and generates a quantum state psi which we desire. We can use random circuit to study quantum scrambling, and in this kind of scenarios, we have one important question in mind. How does information spread in quantum circuits? Majority of work use generic gates to study entanglement growth, which we know grows linearly until it gets saturated, and also to study operators spread. In our paper, however, we have one central question. Does the internal structure of the gate matter? So instead of considering 2-qubit gate, for example, Haar random unitary operators, we consider entangled graph state building blocks. So each of these building blocks are presenting as a graph state with the internal structure of the Clifford gates we use to construct a graph state, and they have a graph representation. So with that, we provide a model, random circuit with graph state building blocks. We choose a graph state of size n. In this example, we have size 5. We inject it in a random quantum circuit with periodic boundary condition and with open boundary condition. We discuss all of these scenarios in our paper. We allow the quantum circuit to go until layer T. The circuit architecture is identical. However, the graph structure changes. So when we compare different random circuits, the structure of the building blocks of the graph states are different from each other. We wanted to discuss and study hierarchy of scrambling. Therefore, we studied two diagnostics of scrambling. One, entanglement velocity, which measures how fast quantum correlations grow after T layer in the quantum circuit. The second is operator spreading, which measures how fast local operators spread. Out of time order correlators reveal the light cone of the operator when it spreads through the quantum circuit. Let's discuss these scramblings with more detail. First, entanglement velocity. We notice that entanglement grows linearly until it gets saturated for all of the graph state. However, the slope depends strongly on the graph state building blocks. All of the comparison and are provided in our paper. The second scrambling, operator spreading. Out of time order correlators detect when an initially local operator reaches a given site in the quantum circuit. Different graph state building blocks produced different butterfly velocity, and all of the comparison, as I mentioned, presented in our paper. We notice one important comparison. For a given graph state building block, we can have entanglement velocity goes faster, however, operator spreading goes slower. Here is an example that I'm presenting for you. For the 6-qubit graph state, here, these two examples, one of them, the entanglement velocity goes faster, which means the subsystem becomes correlated faster within the quantum circuit. For the other one, however, the operator spreading goes faster, which says the local perturbation affect distance sites faster compared to the other building block. We also wanted to show that entanglement velocity and operator spreadings are connected to the internal structure of the building blocks. Therefore, we needed two descriptors for connecting to the internal structure. One descriptor is tied to entanglement growth. So correlates with the entanglement profile. We measure the entanglement across internal cuts. So the building block of the graph state, which has more entanglement across internal cuts, therefore it has a higher rank for the entanglement growth. And this is also connected to the height function. The second descriptor tied to the operator spreading, which counts edges crossing the internal bipartition. For the given graph state, We check how many edges are connecting the first qubit with the rest of the graph state, the first 2 qubits with the rest of the state of the qubit of the graph state, and so forth and so on. And this tells us how fast a local perturbation affects distance signs. Now, allow me to present a summary of our work. Our model discussed random circuit with graph state blocks. Different graph state blocks generate different scrambling speed. We needed 2 descriptors to clarify the hierarchy. We also notice that absolutely maximally entangled graph state blocks maximize entanglement growth in all of the cases that we discussed and studied in our paper. However, not necessarily operators spreading. So if you are interested in this result, I am also happy to announce that my grant application for a 5-year grant from BMFTR was successful. Therefore, I'm looking for a PhD and postdocs with different experience level, working on many-body entanglement and quantum error correction. So if you are interested, please write me an email. All of the codes and numerical results are provided an open access QR code. And with that, I would like to thank you for your attention.